Hello viewers, welcome back to our series of lectures on molecular spectroscopy. In this course, we have so far talked about the general aspects of molecular spectroscopy, wherein we defined spectroscopy to be interaction of radiation and matter. Thereafter, we talked about what is radiation, then what is matter. Then we talked about the quantum mechanical nature of matter, wherein we talked about the quantization of rotational, vibrational and electronic energy levels of molecules. Then thereafter, we talked about how the two can interact. That means, there are different modes of interaction. That means, the radiation is absorbed, emitted or gets scattered, and the consequent the kind of spectra we get from there. And thereafter, we did even talk about the characteristics of spectrum, that is the position, the intensity, the width, and what are the factors that determine that. So, having talked that much, we moved on to rotational spectrum, wherein we considered the rotational motion of diatomic molecule to be that of a rigid rotor. We started with that. We found that quantum mechanically speaking, such a system will have quantized energy levels, and then we realized that this needs modification. We brought in the centrifugal distortion correction there, and then we saw that what kind of spectrum we get there, and then how can this spectrum be used to determine the bond length of small molecules and things like that. Now, today I want to move on to vibration spectroscopy. In vibration spectroscopy, basically what I am going to do today is that I will start with defining what is vibration spectroscopy. Thereafter, we will try to see how do we model the molecular vibrations, and in the process we will just briefly touch upon the results we obtain by treating harmonic oscillator. Thereafter, we will see that this treatment of molecular vibration in terms of harmonic oscillator happens to be inadequate, and that inadequacy can be addressed by introducing what is called as an harmonic nature of the vibration, wherein we bring in the Morse potential and things like that. And then we will try to compare the results what we get by considering vibrational motion to be harmonic and anharmonic, and then see how the two compare, and towards them we will try to sum up what we do today. Let us make a beginning by defining what is vibration spectroscopy. Vibration spectroscopy basically is a study of the consequences of interaction of electromagnetic radiation in the IR region with the molecules. And what happens is, this interaction of IR radiation with molecules causes the transitions amongst the vibration energy levels. That means, that we know that in the molecules the vibration energy levels are quantized. So, this IR radiation causes transition amongst them. That is why it is called as vibration spectroscopy. And since the interaction will result into a spectrum, the spectrum what we get is called as a vibration spectrum, because it is as a consequence of the transition amongst the vibration energy level. Now, let us see how do we model molecular vibrations. I am sure that we understand a vibration, but basically happens is there are two atoms, say atom A and atom B, they are linked together by a bond. So, what happens is these two atoms vibrate. So, this motion has to be considered there, and what we do is, since in this case there is an extension of a bond, compression of a bond. So, this is something which can be considered to be as if the two atoms are joined through a spring. That means, that atoms can be considered as balls which are linked together by a spring, and then that kind of a motion I am talking about. Let us see pictorially how do we represent that. Now, suppose there are two atoms A and B, they are linked together by a spring. Now, what happens is, if I stretch the spring, so this B comes somewhere here, A comes somewhere here, that means you are just expanding it, or you contract that. So, that is the kind of motion we are talking about. So, that is the starting point for any treatment of molecular vibration, and we start with the simplest possible molecule, that happens to be a diatomic molecule, because if we go for larger molecules it becomes difficult. Okay. So, we start with a diatomic molecule and consider it to be oscillating around the mean position. Now, that is a better representation of it. That means, this is the equilibrium position, and if I stretch it, that is a kind of extension we can have, or we can compress it as compared to the equilibrium position. So, that is a kind of motion we are talking about. Now, this kind of a motion is similar to what happens if I just take a spring and try to push it there. Now, what happens is When I suppose I hold one atom here and take the other atom and push it away. So, when I do that, when I extend it, so there is some kind of a restoring force comes into play, that can be expressed in terms of Hooke's law, which says that force is equal to minus k r minus r equilibrium, where F is the restoring force, k happens to be the force constant, r, as I said earlier, is the internuclear distance or the bond length, and r equilibrium is the equilibrium internuclear distance there. Now, what you see is that is the direction of the restoring force is opposite to that of the displacement. What it means is, if I am holding one atom here, if I take the other one, I try to push it, extend it further, so the restoring force will go towards the other atom, and if I am trying to compress it, the restoring force will be in the opposite direction. So, that is what Hooke's law says. If that be so, the energy of such a molecule, what I am showing here is that on this side, well, there are two atoms here, atom A and atom B. I have fixed atom A and I am trying to see if I try to move atom B, then what happens to the energy. So, this is my starting position or the equilibrium position. If I extend it, say I go from here to here, if I express it like this, we find that energy is increasing, or if I compress it, again I find that energy is increasing. And what I find is this kind of a behavior is similar to, is a kind of a parabolic behavior, and the energy expression can be given in terms of minus of 1 by 2 k r minus r equilibrium squared. So, let us see a small animation. Now, what basically is happening is that two atoms are approaching each other. As the two approach each other, the energy is decreasing. When they come to some equilibrium distance, the energy comes to be minimum. If you try to push them through further, the energy starts increasing. This is a familiar thing which we all know from our school days. So, why I am talking about that? Why I am talking about that is because it is something similar here. There also we found that if I have two atoms here, say atom 1, atom 2, this is the nucleus, this is the electron here, nucleus and the electron there. And when the two are far apart, energy is 0. As they come closer and closer, so this electron and this nucleus start attracting, this electron gets attracted by this nucleus and energy starts decreasing. As we come to some equilibrium distance, the energy comes to minimum. If I try to push it further, then what happens is the energy starts increasing. Something similar to what we are having here. When a molecule is vibrating, so this vibrational frequency of the bond will depend on two things, the force constant and the reduced mass. And the expression is very simple, that is omega oscillation is equal to 1 by 2 pi square root of k by mu hertz, where mu happens to be the reduced mass. I am sure that you all know what reduced mass is. It is a simple expression over there. Now, typically what we do is we try to express it in terms of spectroscopic units, wherein we try to express it in terms of centimeter inverse. To do that conversion, what we do is, if I divide this by c, omega oscillation bar happens to be 1 by 2 pi c square root of k by mu in terms of centimeter inverse. So, what you find is that the oscillation frequency, that is a basic frequency at which the bond is oscillating, depends on two things, because pi and c happens to be constant. It depends on the force constant k and mu, the reduced mass. Force constant is basically the measure of the strength of the bond. Let us take some examples to understand this. If I look at these three examples there, so I am talking about C single bond, carbon carbon single bond, carbon carbon double bond, carbon carbon triple bond. We know that double bond is stronger than single bond, which in turn is triple bond is stronger than the double bond there. And accordingly, what you find is that the oscillation frequencies are in the increasing order there. So, 1200 for CC single bond, 1650 for double bond and 2150 for the triple bond. That means, as k is increasing, in all the three cases mu happen to be the same, because the two atoms are identical in all the cases. So, in this case, in this example, what we see is that as the strength of the bond increases, so does the vibrational frequency. Let us take the second case. Now, here what we have is, we have got a series of bonds shown here, wherein one atom happens to be carbon, which is fixed, and in this case it is hydrogen, it is CH, CC, CO, Cl. So, what we are doing is that we are trying to take one atom to be constant and the second atom is getting heavier and heavier. We start with hydrogen, we come to carbon, to oxygen, to chlorine, and we find that as mu is increasing, the vibration frequency is decreasing, because there is a inverse proportionality there. The formula tells us it is square root of k by mu. So, mu is in the denominator. So, that is the kind of trend we have. So, there are two important things just to make an estimate. If I want to compare two bonds and see that which is going to have a higher vibration frequency, we can very simply do that with this simple formula. Okay. Now, let us move further. If I take my molecule which is vibrating and I assume it to be vibrating as a harmonic oscillator, as I just explained. That means there is a harmonic kind of a vibrations there. If I treat that problem in terms of quantum mechanics, that means basically you formulate a Schrodinger wave equation and then solve it and do all kind of things which we done in the quantum mechanical course. When we do that, we find that this vibrational motion is quantized, and what we get is we get a series of energy levels which is given as EV. V happens to be the vibrational quantum number which has a value of 0, 1, 2, 3, 4 and so on and so forth, and the expression happens to be EV to be equal to V plus half H omega oscillation in terms of joules. And here again what we do is we try to express it in terms of spectroscopic units, wherein I want to use as centimeter inverse. When I do that, I just divide this EV by Hc. So, I get epsilon V, that is the energy expression in terms of spectroscopic unit, and that will come out to be, I just make a simple substitution, this H gets cancelled out here, and what I will get is I will get V plus half omega oscillation in terms of centimeter inverse. What does this expression mean? How does it translate into an energy level diagram? Let us try to see that. If I substitute different values of vibrational quantum number, say V is equal to 0, I get the first energy level, that happens to be at 1 by 2 omega oscillation. If I put V is equal to 1, I get 3 by 2 omega oscillation, and so on and so forth. So, what we find is that we get a series of energy levels which are equally spaced. That means, if I take the difference between any two consecutive energy levels, it will come out to be omega oscillation. That is the kind of situation I come across if I consider my molecule to be vibrating like a harmonic oscillator. So, that is a kind of a outcome of this model. Now, if I try to analyze this slightly closely, what you find is that you get a very interesting observation here. That is, when V is equal to 0, we find that E0, that is the ground state energy, happens to be 1 by 2 omega oscillation. This energy is called as the 0 point energy. This is an outcome which is a consequence of the wave mechanical approach to the vibration motion here, because classically speaking, a vibrating molecule may have 0 energy, but quantum mechanically what we come across is that the molecule cannot have a 0 vibration energy, it has to have certain minimum, that minimum happens to be 1 by 2 omega oscillation. Now, what does it mean? This 0 point energy actually depends on the classical vibration frequency, that is omega oscillation, and also this is non-zero, that is very significant. That means, in principle, quantum mechanically speaking, the molecule can never be at rest, because for a molecule to be at rest, the energy must be 0. You remember that in case of rotational spectroscopy, when we talked about the energy expression, when we worked on that case, we found that when J is equal to 0, E is equal to 0. That means, a molecule may not rotate at all, that means J can be 0 there, but for V is equal to 0, we find that energy happens to be non-zero. This is a very significant contribution which comes by the wave mechanical approach to molecular vibration. Now, let us move on further and see that what is the kind of a necessary condition required, because we have seen that how to talk about molecular vibration as a harmonic oscillator to begin with, and we find that this motion is quantized, we got an energy expression there which translates into energy level diagram. But now, for the molecule to interact with IR radiation, we need certain kind of prerequisite, and the prerequisite happens to be that if a molecule is vibrating or oscillating, it must be associated with some kind of a fluctuating or oscillating dipole moment, because this oscillating dipole moment which the molecule will generate will interact with the oscillatory electric field of the EM radiation, then only the two can interact and we can get a resultant spectrum over there. Let us take the case of a homonuclear diatomic molecule, say hydrogen. We find that hydrogen does not absorb IR radiation. On the other hand, a heteronuclear diatomic molecule like HCl does. Let us see the reason for that, because hydrogen molecule is non-polar. I mean, if this molecule vibrates, that means if the bond expands or contracts, in no case does it generate any kind of dipole moment. On the other hand, HCl is polar to begin with, and if I expand this bond, we find that the dipole moment increases. When it contracts, the dipole moment decreases. So, as a consequence, when this molecule vibrates, we find that there will be an oscillating dipole moment which will be kind of in a position to interact with the electrical component of the EM radiation, and there will be an interaction there. Let us take the case of carbon dioxide. I am talking about one of the vibration modes of carbon dioxide, wherein suppose I am looking at this molecule of carbon dioxide. So, this is carbon here and the two oxygens. So, carbon is shown with a red ball and oxygens are shown by the two small black balls. There is no dipole moment because this bond is polar, so is this bond. The dipole moment of these two polar bonds are in the opposite direction, so net dipole moment is 0. Suppose there is an asymmetric vibration, whereas one bond is expanding, at the same time the other bond is contracting. Now, the dipole moment dimensions or the magnitude of two dipole moments are not equal. So, they do not cancel out, there is a net dipole moment. We find that there is a dipole moment in this direction. Now, when this comes back to same position, so again I have got no dipole moment there, and if it happens the other way around, that means this bond expands, the other one contracts, the dipole moment direction is reversed now. So, we find that if a molecule of carbon dioxide is undergoing an asymmetric stretching vibration, that means one bond is expanding, the other bond is contracting at the same time. If that happens, then this generates an oscillated dipole moment, and this can interact with IR radiation, and this mode of vibration of carbon dioxide is IR active. We will talk more about it at a later stage. Now, let us move further and see that having talked about what are the prerequisites, let us now move on to the selection rule. Selection rule is very simple. We know that selection rule tells us about the condition, whether the transition will be allowed or not. If we have energy levels and the radiation also is coming, but will the transition take place or not, and that is determined from quantum mechanical treatment. We find that for a harmonic oscillator situation, that delta V happens to be plus minus 1. That is, as per the quantum mechanics, the transition amongst the vibration energy levels can take place only when delta V happens to be either plus 1 or minus 1. What the mean is that in terms of this selection rule, the transitions which will take place, say I take some energy level, say V, and I am talking about transition from V to V plus 1 level. So, this energy can be computed as, I just substitute the value of V plus 1 here and substitute the value of V here. That means, this is energy of V plus 1 level, this is energy of Vth level. If we do this subtraction, we find it happens to be omega oscillation. That is straightforward. That means, the spectrum will consist of only one single line at vibration frequency, that is omega oscillation. Now, let us raise a question, that is, so far we considered that vibrational motion as a harmonic oscillator, but is it a true picture? Does it give a true picture of the molecule? Let us try to have a look at it. Now, let us try to have a look at it. Suppose I got a molecule, this is atom 1, atom 2. Okay. Now, I am keeping this atom fixed and I am trying to vibrate this. Okay. What essentially is happening is that at this my equilibrium position, if I give some and it is vibrating, that because no molecule is stationary, it is vibrating with certain amplitude. If I give energy to this, so I am holding this here, so this will vibrate, the magnitude of oscillation will increase. If I give still more energy, this will still stay there, this will become still larger. Okay. That means, if I keep on giving more and more energy, the amplitude of vibration increases, but if I give extreme amount of energy, it will still be able to stretch a lot and come back. That means, in principle, if I am considering a harmonic oscillator, if the molecule is vibrating the way a harmonic oscillator does, then the molecule will never dissociate. But we know that the molecules do dissociate. That means, there is some kind of an anharmonicity there. That means, this model which we have considered is inadequate. We need to make some amends to this, and that can be incorporated. This anharmonicity or the anharmonic behavior of a vibrating molecule can be accommodated by using a different kind of potential. We took Hooke's model to Hooke's equation to begin with, and then we use the expression of energy which comes from there. But now what we find is that we need to consider Morse potential. Morse potential is given by the following expression. This parabola is what we considered earlier as a harmonic oscillator, and this line here, this is something similar to what we had seen in the case of bond formation there. That is the Morse potential curve. If I consider this, we find that the molecule can be shown to dissociate if I give enough energy to that. That means, if I start giving energy, we find that there will be more of expansion and then less of contraction. If I go beyond this energy, the molecule will dissociate into the constituent atoms there. So, that is a kind of a potential we have to consider. If I do so, what happens if I change the potential? If I change the potential, we find that the energy expression gets, that means basically what I am doing is, I instead of considering harmonic oscillator, now I am trying to talk about an harmonic oscillator. and treat the problem in terms of quantum mechanics, we find that the energy expression gets modified. So, what we have now is E v to be equal to V plus half omega E minus V plus half square omega E x e. This omega E is the equilibrium oscillation frequency and x e happens to be an harmonicity constant. That is a kind of a correction term which comes in over there. If I can simplify it here, so I get is omega E and then 1 minus x e and so on and so forth. So, that is a kind of expression I get, contrast to what we had in case of our harmonic oscillator. Now, second thing what happens as a consequence of considering as the potential there, we find that our selection rule also gets modified. The selection rule now becomes plus minus 1, plus minus 2, plus minus 3, which in turn means that I can have large number of transitions possible there. I can have 0 to 1, 1 to 2, 2 to 3, 3 to 4 or 1 to 3, 1 to 4. You can have all possible transitions there because there is no limit anymore. Whereas, in case of harmonic oscillator, we had delta V to be equal to plus minus 1. That means, we can just go from one level to the next one. And harmonic oscillator, we find that the number of lines or the bands affected is much larger. That is a drastic change when we move from harmonic to anharmonic oscillator. Now, let's try to compare what kind of expressions we get in the two cases. One thing we see is our energy in case of harmonic oscillator was V plus half omega oscillation, whereas in case of anharmonic oscillator it is omega E 1 minus x e V plus half and so on and so forth. If I compare, I find that omega oscillation happens to be omega E 1 minus x e V plus half. What does it mean is our vibration frequency is decreasing as V is increasing, x e happens to be the correction term in that. So, oscillation frequency decreases with the increase in the vibration quantum number, that is V. If I take it to be minus 1 by 2, this gets cancelled out, it becomes 0. When this becomes 0, what do I get? I get omega oscillation to be equal to omega E. So, this omega E is called as equilibrium vibrational frequency. It is a hypothetical term because you cannot have V is equal to minus half, because as per quantum mechanics, V happens to have the value of 0, 1, 2, 3 and so on and so forth. I am just taking it hypothetically. If my V happens to be minus 1 by 2, that will be called as the equilibrium oscillation frequency. Now, let us go further and make further comparison between the two models here. If I take the ground state, oscillation frequency in case of an harmonic oscillator happens to be omega E 1 minus 1 by 2 x e. This expression I get just by substituting V to be equal to 0. In case of my harmonic oscillator, it was just omega oscillation. So, we find that oscillation frequency for a harmonic oscillator and harmonic oscillator are different, and this is a kind of a correction term we have here. Secondly, if I look at a 0 point energy, the 0 point energy in case of an harmonic oscillator will now be given as 1 by 2 omega E 1 minus 1 by 2 x e, which again is different from what we had in case of harmonic oscillator, just 1 by 2 omega oscillation. So, we find that the expressions for the two cases happen to be different here. That is, the 0 point energy is slightly less than what happened in case of harmonic oscillator. So, we are seeing the consequences of moving from harmonic oscillator system or model to an harmonic oscillator model. So, let us try to now sum up what we done today. What we done today is we discussed how to model a molecular vibration. We talked two kind of models there. One was harmonic oscillator and second happened to be anharmonic oscillator. Then we stated and analyze the results of quantum mechanical treatment of harmonic oscillator. We realized that if I treat my molecule to be behaving as a harmonic oscillator, what kind of energy expression I get and what are the corresponding energy levels and what kind of spectrum do I come across. Thereafter, we showed that this harmonic oscillator model is inadequate because this does not account for the fact that if I give energy to the molecule dissociates. If I consider the molecule to be harmonic oscillator, it will not dissociate at all. So, it was inadequate. So, we brought in the concept of anharmonicity into the model and we found that as a consequence of that our energy level expression changed and so did the our selection rules. And towards the end we try to compare the outcomes of harmonic and anharmonic oscillator models. Now, in the next session we will go into more details of it. We will see that if I have, because my true picture is closer to an harmonic oscillator, if I consider that, what kind of spectrum do I expect? And so far we have just been considering a simple diatomic molecule, but what will happen if I have a polyatomic molecule? How many signals do I expect and how do I make use of those signals? So, that all will be taken up in the next session.